All right, this is the second half of Unit 6.6, the quadratic formula, the nature of the roots. So in the first video, we talked about the quadratic formula, and at the end, we looked at the roots. So the quadratic formula is really easy to use. You just substitute numbers into the equation. It also gives us some indication as to what's called the nature of the roots without actually solving for the roots. And what I mean by the nature of the roots is basically how many are there, and are they real numbers or aren't they? So if you remember from the last video, hopefully you watched the whole thing, we decided you can have two answers, you can have one answer, two real numbers. You could have one real number because the two answers that you get are the same answer. Or you could have no real roots. And in this case, actually, because you have to add the root negative 56 and you have to subtract the root negative 56, there are still two answers, but they're not part of the real number system. They're part of that whole extra system that I talked about called the complex number. So there's two real roots, zero real roots, but there are actually two complex roots. I don't really want to get too much more into that. When you give me an answer, you can say zero real roots because we're only dealing in the real number system. We only want to deal in the real world. We're not trying to deal in the complex world, okay? Just the real world. Okay, so part of the, so we can determine how many solutions there are to one or no real roots and how they relate to the graphical representation of a simplified equation. So in the quadratic formula, the thing that is going to determine for you without actually having to figure out what the roots are is this stuff underneath the square root sign. Again, when we go back to these four examples back here, when we did the square root in this example, it turned out to be the square root of 129. And we ended up with two roots. This one here ended up to be the square root of 137. And we ended up with two roots. This one, however, ended up to be the square root of 0. And we ended up with one root. And then this last question ended up being the square root of a negative value. And we ended up with 0 real roots. So if we just take a look at that stuff underneath the square root sign, which is just the b squared minus 4ac, that will tell us the nature of the roots. So how many are there? How many real roots are there? So if b squared minus 4ac, if that turns out to be a negative value, so it's negative, turns out there are 0 real roots. If b squared minus 4ac equals 0, you guessed it, there is 1 real root. And if b squared minus 4ac is greater than 0, that means that you get 2 real roots. And I'm going to tell you a little bit extra right now. If b squared minus 4ac equals a perfect square, whoops, that's not how you spell perfect. Perfect square, that means then the quadratic, can't spell anything right now. It's Friday afternoon, by the way. I don't know if you know that, but I guess you wouldn't. Why would you know that? You don't know when I record these lessons. So it is Friday afternoon. In fact, it's 4:20 on a Friday afternoon, and I've been doing this all day. So I'm getting a little bit antsy here. Quadratic. That's not even, why I didn't even spell it right there. Okay. Okay. Quadratic. That doesn't even look like. Yeah, that's right. Then the quadratic was factorable. So you could have solved it by factoring. But it has to equal a perfect square. So what's a perfect square? Well, that's a number like 4, 9, 16, 25, 36, 49, 64, 81, 100, and so on. I mean, it could be a huge number. You just square root it, and if you get like a nice, pretty number, then you're good. It was factorable in the first place. So that's just a little bit extra. So if you ever want to test to see if you can factor something, then you do b squared minus 4ac. If that's a perfect square, then you could have factored it to solve it. You don't have to use the quadratic formula, but I mean, you can always use the quadratic formula. Okay, so how many roots are there going to be? Again, I don't want you to solve. I just want to know how many real roots there are. So we're just going to do b squared minus 4ac. So b is equal to negative 5, so that's negative 5 squared minus 4 times 3 times negative 9, which equals positive 25 plus 4 times 3 is 12 times 9 is 108, which is equal to 133, which is greater than 0. So go back and take a look. Hopefully you say that's 2 real roots. Okay, we're just going to do the same thing again. B squared minus 4ac equals, b is negative 6 squared minus 4 times 1 times 9. That is positive 36 minus 36, which equals 0, which equals 0. You guessed it, 1 real root. And the last one, b squared minus 4ac equals negative 5 squared minus 4 times 7 times 2, which is 25 minus 4 times 2 is 6 times 7 is 42. No, sorry, 4 times 2 is 8. It's late. Times 7 is 56. 25 minus 56 is negative 31, which is less than 0, and that means 0 real roots. But it also means there's 2 complex ones. Again, you don't really have to do that, but you do need to know it's 0 real roots. Okay? For what values of k will the following have 2 real roots, 1 real root, or no real roots? For it to have, let's start with 2 real roots. For that to be true, then b squared minus 4ac will have to be greater than 0. So 4 squared minus 4 times 3 times k will have to be greater than 0. So 16 minus 12k will have to be greater than 0. And you can either bring the 16 over to the other side, or you can bring the 12k over to the other side. If you bring the 16 over, then we need to talk. If you're going to bring the 12k over, then we don't. But we're going to need to talk anyway, because you need to know what I'm talking about. Let's say I move the 12k over to the other side. So let's say I do it this way. 16 minus 12k is greater than 0. Bring the 12k over, so 16 is going to be greater than positive 12k. Divide both sides by 12, and then you get 16 divided by 12 is 4/3. So k is less than 4/3, or 4/3 is greater than k. So therefore, k is less than 4/3. Okay, now what happens if I bring the 16 over to the other side? So 16 minus 12k is greater than 0. Minus 12k is greater than minus 16. Okay, watch what happens. I divide by negative 12. I divide by negative 12. K is greater than 4/3. Wait, that's not what this said. This is k is greater. This is k is less. There's something wrong with that. Okay, so here's what's wrong. This thing here, you haven't done this before, but this is called an inequality, also known as a greater than sign. And when you are solving an inequality, you solve it just like an equation, a linear equation, because the k is not, we're trying to solve for k and the k is not being squared. So this is a linear inequality. And to solve a linear inequality, you want to solve it just like a linear equation. You want to get all of your, in this case, your k terms on one side and all of your non-k terms on the other side. Here's the only extra rule that makes it ever so slightly different from solving a linear equation. If you divide by a negative, you need to switch the signs. So if you divide, actually, or multiply, because dividing by a negative is the same thing as multiplying by its reciprocal. Multiply by a negative, switch the sign, of the, switch, let's change this. Switch the direction of the inequality. Switch the direction of the inequality. So because I divided by negative 12 here, instead of this inequality being a greater than, it's now actually going to be, let me do this in a different color. It's now actually going to be a less than. So now I do have the same answer as I did over there. Okay, up to you how you want to do it, if you want to put the 12k on the left and 12k on the right. But you need to remember that if you are going to divide by a negative, you've got to switch the direction of that. Now there's an algebraic reason behind it that I'm not going to get into. You're going to do more inequality stuff when you get into grade 12. This is as far as you need to know right now. If you divide or multiply by a negative, you need to switch that sign. Okay? All right, that's it for that. Now, if a quadratic equation is in factored form, so now we're just talking about nature of the roots. We're not talking about the discriminant anymore. We have completed everything that we need to know about standard form. So ax squared plus bx plus c equals 0. You use the discriminant to determine the nature of the roots. So now we're going to move into, okay, well, what if it's not in standard form? What if it's in factored form? So now how do we determine how many roots there are? Well, the roots are the x-intercepts, right? Well, how many x-intercepts are there here? If it's in factored form, then you have one x-intercept at 4, and you have the other x-intercept at -1/2. So there's 2 real roots. For this one, oh, that should say equals 0. For this one, you have x equals -4. Remember, this means 5x plus 4 times x plus 4. Both of these brackets are the same, and they're both going to yield a 0 at -4. So there is 1 real root. Factored form is awesome. It tells you right away, just by looking at it, how many roots there are. And I've alluded to this several times before. If there are no x-intercepts, then there is no factored form. So, factored form is not possible when there are no real roots. So you'd never have a question in factored form where there are no real roots. There's got to be 1 or there's got to be 2. That's the only choice that you have. Okay? All right, so that's it for factored form and nature of the roots. Again, we didn't need to solve for these 2 roots, or we didn't need to solve for this one. We can see by the fact that there's those 2 brackets right there that tells us there's 2 roots. There's this 1 bracket there, that's 1 real root. But don't get this confused with a single bracket. Like if it said 5x plus 4 squared and then -3, that's not factored form. That's now vertex form. Or if it's, so we've got to look at a different, that's what's coming next, vertex form. Or if it said 5x plus 4 squared minus 3x, well, that's not even vertex form. That's not vertex form. That's not factored form. That's nothing. And you've got to expand and simplify to get it into standard form and then use the discriminant to determine the nature of the roots. Okay? So factored form is very specifically a number times a bracket times a bracket. Nothing added or subtracted after that. Okay? Nothing added or subtracted after that. Standard form, no brackets at all. It's ax squared plus bx plus c. That's it. No brackets, nothing at all. And then finally, vertex form has brackets, but it has brackets, so a number times the bracket squared plus a number. That is definitely vertex form. So now we want to look at the nature of the roots when it's in vertex form. So now we're going to think about what does that parabola look like. So can we all agree if I have a parabola and then I just move it left or right, which is really done by the H, right? Moving it left or right is done by the H. The A tells you what the shape of it looks like. The K tells you vertically where the vertex is. But if I take and I move it left or right, so if I take this and I move it over to the right, I still have two roots. I had two roots to start off with. I move it over, I still have two roots. I move it over to the left, I still have two roots. If I had no roots to start off with, so let's say it looked like this, no roots, I move it left or right. Let's say I move it over here. It still has no roots, or I move it over here. It still has no roots. There's moving it left or right. The H has nothing to do with how many roots there are. Absolutely nothing to do with that. So what we want to look at then is the A and the K. So remember, the A tells you the direction of the opening. Oh, and also how wide or narrow a parabola is not going to tell you whether it has 0, 1, or 2. So I could have, let's say this is the vertex. I could have a really narrow parabola, which will have opening up, which will have 2. I could have a really wide one with the same vertex. It has 2 roots. I could have an even wider one. It's going to have 2 roots. So how wide or narrow the parabola isn't going to determine how many roots there are. What does determine how many roots there are is the direction of the opening. So direction of the opening and the K value. So is the vertex above or below the x-axis? So remember, if K is greater than 0, that means it's above. If K is less than 0, that means it's below. Okay, so we've got direction of the opening, which means if A is greater than 0, that's opening up, and if A is less than 0, that's opening down. So we got 4 different situations to look at. When A is greater than 0, and then the 2 different K's, and then when A is less than 0 and the 2 different K's. So let's say A is greater than 0 and K is greater than 0. How many times is that parabola going to cross the x-axis? So it's opening up and it's above the x-axis. What do you got for me? Hopefully you said no real roots. H doesn't matter. Okay, let's keep, let's go, if A is greater than 0, keep A greater than 0, but now K is less than 0. So it's opening up, but the vertex is below the x-axis. What's that happening? How many times is that going to cross the x-axis? So it's opening up, but the vertex is below the x-axis. Well, clearly you can see by my diagram that it's going to cross the x-axis twice. So that's 2 real roots. Okay. Let me erase that. Okay, what if A is less than 0 and K is greater than 0? So it's opening down, and K is greater than 0, so that means it's above the x-axis. Think about it. Okay, hopefully you said 2 real roots. Okay, now what if A is less than 0 and K is less than 0? So it's opening down, and it is below the vertex is below the x-axis. So it's opening down, and the vertex is below the x-axis. How many x-intercepts? You are right. There are no real roots. Okay, is there anything we haven't thought of? Oh, I can think of something we haven't thought of. What about if A or K are 0? Well, if A is 0, this isn't even a quadratic anymore. So if you recall, way back when I first introduced so ax squared plus bx plus c, A can't equal 0. And I don't care what form you're in, A x minus r x minus s, or A x minus h squared plus k. A can't equal 0. If A equals 0 here, that term's gone. All you have is a linear left. If A equals 0 here, this whole thing equals 0, and you just have a straight line, which is the x-axis. And if A equals 0 here, this will be gone, and you have a straight line at, they're all straight, sorry, a horizontal line at y equals k. So A can't be 0 in a quadratic relationship. So we don't care about A equals 0. What if K equals 0, though? What does that mean? If K equals 0. So remember, K is the vertical translation of the vertex. So if K equals 0, that means that the vertex isn't above or below the x-axis. So if K equals 0, how many roots are there? K equals 0, the vertex is sitting on the x-axis. It might be opening up and it might be opening down. I don't know. Who cares? How many solutions are there? That's right, there's 1 real root. Okay, so a summary of all this. Notice there are no real roots here if A is greater than 0 and K is greater than 0, and there's no real roots here if A is less than 0 and K is less than 0. So if they're both positive, or they're both negative, or what happens if you take 2 positive numbers and you multiply them, or you take 2 negative numbers and you multiply them? You're going to get a positive. So if A times K is greater than 0, there are no real roots. If A times K is less than 0, there are 2 real roots. And if A times K equals 0, there's 1 real root. To be honest, I would never memorize this part. I would just think about what's going on. In fact, I've never used this over here before. Well, I've talked about it before. But when I'm looking at an equation, so let's say you look at negative 2x minus 4 squared plus 7. This is opening down, and this is above. That's 2 real roots. Or if you have negative 3x plus 4 squared, this is also factored form, right? This is 1 real root. That means that you're adding 0. That means that it's not above or below. This is 1 real root. Doesn't matter if this is a plus 3 or a minus 3. It doesn't matter the direction of the opening in this case. Okay, so here's your homework. Page 342, numbers 1, 2, and 9. This all is on the quadratic formula. And page 350, 3ABD, 4ABC, 5 and 9 and 10. This is all on the nature of the roots. Okay, that's it. Again, if you have any questions, please contact me.